Hey guys, it's Mr. Oliver. Today I'm going to go over the solutions for the Unit 4 free response practice. Let's start with problem number 1 first. Okay, so in this question, we've got two spheres, one that has a mass of 3m, one that has a mass of m. So you can imagine maybe this is like a basketball, and maybe you've got like a foam Nerf ball or something on top of it, or maybe it's a basketball and a tennis ball, something like that. And so you're going to drop it from some height of h, and it's going to hit the ground, and then afterwards they're going to bounce. All right. Now it says that they're simultaneously dropped from rest, and usually you would assume that the air resistance is irrelevant on this. You would also assume that the acceleration due to gravity is g. And it tells us that specifically we need to express all our answers in terms of capital M, capital H, and fundamental constants as appropriate. So question A is pretty straightforward. It says derive an expression for the speed, VB, with which the large sphere strikes the floor. And so this ball right here is going to come down and hit with a speed of VB in the first part. Okay, so that's pretty straightforward. What we need to do is use conservation of energy. You could also use kinematics if you wanted to, but conservation of energy is a lot easier. So our initial energy type will be the fact that it's above the ground of a height of h. Okay, so that's our potential energy due to gravity. And our final energy type, of course, will be kinetic. Right before it hits the ground, it is moving. So we've got the expression mgh for potential energy and 1/2 mv squared for kinetic energy. Now, in this case, the mass appears on both sides of the equal sign, so they both cancel. And so that means our velocity is going to be the square root of 2g times the height. Well, they give us a capital H, so I need to make sure I use a capital H. And they're saying what's the velocity of the ball, so I'm going to put the little subscript b down here for v ball. And that is worth 2 points for part A. Part B asks us to find the equation that relates VB, VS, and VL. So what's happening at this point is after they hit, this lower sphere is going to hit the ground first. And because it hits the ground first, it's going to change its direction from going down to back up. And it happens really quick because this guy's right behind it. I mean, it's almost, it's almost essentially touching it. And so what happens is the lower mass, the 3m mass, is going to be moving up, and the upper mass is going to be moving down. So it's almost like there's a collision. Like this one moves up, this one moves down, and there's like an elastic collision. And if you remember, for these collisions, the momentum will be conserved. And so when I set this up, I'll kind of show you what I'm talking about. I've got a lower mass down here, which is 3m. I'm going to call this ball number 1, and it's going to be moving upwards. And then I've got this other mass, which I'm going to call ball number 2, and it's going to be moving downwards. Now, it tells us some information about this. This lower mass, of course, we'll say M1 is a mass of 3m. The upper mass, which we'll call mass number 2, has a mass of just plain old m. It tells us in the problem that the ball, the large sphere, is going to be moving upward with a speed of VB. So it's a perfectly elastic collision here. It goes down at VB and it's going to return up at VB. So I'll say that V1 initial is actually the same thing as VB. And then the sphere number 1, or the second sphere, the smaller sphere, is also moving at VB. So they're making the assumption that these two things have the same speed because they fall from the same height, which makes sense. And so VB is also going to be V2 initial. Sorry, V2 initial. All right? And so this is kind of like before the collision. Now, after the collision, this upper ball, number 2, is going to be moving away, and it tells us in the problem that the small sphere moves upward with a speed Vs, so I will say V2 final is Vs. And then for the larger ball, it tells us that the large sphere has a speed of VL. So I don't know which way it goes let's just assume it goes up. I don't know for a fact it will, but I'll say that V1 final is VL. And so it helps to kind of draw a picture and kind of set up all these variables ahead of time. So now when we want to derive an expression for that, or derive an equation that relates VB, VS, and VL, I can do that using conservation of momentum. So I'll say that P initial, which is the initial momentum of the system, will equal the final momentum of the system for these two things. So let's just set this up real methodically. So I'll have M1 times V1 initial plus M2 times V2 initial equals M1 V1 final plus M2 V2 final. All right, now it is important to remember that these velocities do have direction. They're vector quantities, same as momentum. And so now I can make some substitutions for all these terms. M1 is the larger sphere, so that's 3M. V1 initial is VB, and it's moving in an upward direction, so that's a positive VB. M2 is just M. Okay. V2 initial is moving downwards, so that's a negative VB. Negative VB. M1 once again is 3M. V1 final is VL. M2 is just M, and V2 final is VS. All right, and so there's a couple things that we can do real quick. We can cancel all the M's because they appear in each term, each one of these little clumps. And so we're going to have 3 VB left over, and I've got a minus VB on the left. On the right hand side, I'll have 3 VL plus VS. Now, we're almost done. About the only thing I can do here is subtract 1 VB away from 3 VB. And so I'll have 2 VB is equal to 3 VL plus VS. And that's our solution for part B. It doesn't tell us to solve for anything. It just says to derive an equation that relates those three variables together. And that would be it. Okay. Our next question says, in this particular situation, VL is equal to 0. So what I can do is take my previous equation and set VL equal to 0. So what that looks like is that, this is for part C. I have, on the left-hand side, I had a 2 VB. On the right-hand side, I had a 3 VL plus VS. And the question says, use your relationship from part B, which is this, to determine the speed of the small sphere in terms of VB. Well, in other words, plug in VL equals 0 here. And so sure enough, VS is twice the speed of VB. All right. Part D indicates that we want to indicate whether the collision is elastic. Justify your answer using information gathered from previous parts and correct physics principles. All right, so how do we know if a collision is elastic? Well, elastic collisions, by definition, conserve not just momentum, but they also conserve energy. Specifically, kinetic energy. All right. Now, how do I express that? Well, what you want to do is you want to show through mathematics that the initial kinetic energy is the same value as the final kinetic energy. So we need to show that those two things are equivalent. So it's going to take a little bit of work. So let's go ahead and grind through the initial kinetic energy. Both objects are moving, right? Initially, they're both moving at this point. So this is like right before the collision. So our initial kinetic energy is 1/2 m1 v1 initial squared plus 1/2 m2 v2 initial squared. This is right before the collision. And so we'll have 1/2 times 3m times VB squared plus 1/2 times just plain old m, the second mass of plain old m, times V2 initial squared, which was a negative VB. Now that value gets squared anyway, so that negative sign can go away. And so this is 3/2 m VB squared plus 1/2 m VB squared, which is 4/2 m VB squared. 3/2 plus 1/2 is 4/2, or in other words, 2 times m VB squared. So that's my initial kinetic energy. Now, after the collision, our final kinetic energy is going to be of similar form. We're just plugging in different variables. So it's still going to be 1/2 m1 v1 final this time squared plus 1/2 m2 v2 final squared. From before, from our previous, I guess it's part B, our previous information tells us that m1 will be 3m, so 3m. v1 final was 0. That was told to us in the problem statement. m2 is just plain old m, and its velocity was the velocity of the sphere right here, which is 2 VB. Velocity of the sphere is 2 VB. So I've got 2 VB, and that quantity is squared. And so this term, of course, goes away, and so we're left with 1/2 m times 2 squared, which is 4 times VB squared. And so 1/2 times 4 is 2, and we have 2m VB squared. And so sure enough, those two values are equivalent. So therefore, you can conclude that because they have the same initial and same final kinetic energy, that it is elastic. It is an elastic collision. All right, so that's for part D. Now the last part, part E, says determine the height h that the small sphere rises above its lowest position in terms of the original height. And so for this part, you have the small sphere, which after its launch is moving upwards at a speed of 2 times VB. That was the original velocity after that collision. So it didn't really hit the ground, it hit the large sphere. That's what bounced it up. And so it's going to travel up for that height to some new height h. Right? In which case the kinetic energy at the bottom will transfer into potential energy. So I'm just going to set up a conservation of energy. E initial equals E final. The initial energy type is 1/2 is kinetic, so it's being launched. It's 1/2 m times 2 VB squared. That's my initial velocity, 2 VB right here. And that equals mgh. And so our m's can cancel. 2 squared is 4. So I'll have 1/2 times 4 VB squared. That equals gh. 1/2 times 4 is 2, so I got 2 VB squared is equal to gh. But if you remember from previously, from one of our previous parts, I guess it was part A, VB was actually square root of 2g times big H. So I'll make that substitution in for VB. It gets squared. And so we got 2 times the square root of 2gh times 2. And so that's just going to reduce to 4g times capital H equals gh. And look here, the g cancels. And so h, our new h, is actually 4 times as high as our original capital H. So that smaller sphere will bounce 4 times as high as what it was dropped from. All right, and guys, this is something that you can actually do at home. Go outside, get you a basketball or something bouncy, soccer ball, something like that, and put you something lightweight on top of it, and drop it. And guys, I'm not gonna lie to you. That thing might pop you in the face, so be careful when you drop it. But if you put a tennis ball on top of a basketball, it's going to rocket off really fast, and you'll see how high it goes. It'll go about 4 times as high. All right, so, or depending on these masses, of course, but it's a pretty neat little experiment. You should try it out. All right, guys, that's all for this one. If you have any questions, please shoot me an email. I'd be glad to help you out. Thanks a lot. Bye-bye.